And so then Joe is my middle name, and that stuck. Well, it's a great pleasure to be back in Cambridge. So this is some work done in collaboration with Benjamin Doyle and Andy Lucas and Conrad Charm, who's a string theorist, trying to use methods of ADS-CFT to understand non-equilibrium problems. And I should say that I was scheduled to talk on Wednesday rather than today, so I'm standing in for Sergey, who's probably delayed because of the weather in the US. So I've got more transparencies than I would normally use for a 1-hour talk, so I will skip over some as I'm going along, and so feel free also to interrupt, and I'll try and keep things relatively informal, okay? So what I'll try and do is I'll give a little bit of background and motivation from a condensed matter perspective, why we're trying to use these techniques of the ADS-CFT correspondence, and I'll give a very brief introduction to how these tools can be used and why in particular they're useful for condensed matter problems. And I would say one of the strong motivations for this work was to try and demonstrate that methods of the ADS-CFT correspondence could be useful in condensed matter contacts and actually make contact with exact results known from integrability, but also generalize them to higher dimensions. So obviously we have a lot of exact techniques that work in 1D, but very few techniques that we can use in higher dimensions. And so this was some attempt to try and step in that direction. So the vast majority of the stuff I'll talk about is contained in this paper. We have some very recent work on the archive. Okay, there's actually some minor subtleties associated with the high dimensional solution that I'll discuss. And so I'll try and give a little bit of a balanced overview of these two papers. Okay. So over the last few years, there's been this kind of huge amount of activity in what's become known as ADS-CMT, so trying to apply the ADS-CFT correspondence to condensed matter problems. And for example, there's been a lot of work on looking at, say, entropy and viscosity ratio coming from supersymmetry Yang-Mills theory and trying to apply these ideas to condensed matter problems. Okay? And one of the reasons I'm going to argue that some of these things work is because actually the strongly coupled theories are often described by other overarching principles such as hydrodynamics. And if you therefore take the view that these hydrodynamic principles ought to generalize, it's actually possible for results computed in ADS-CFT to actually give you some kind of orientation and intuition for condensed matter problems. Okay? So what I'll talk about much less is that there's been a lot of activity trying to apply these to difficult problems in condensed matter, such as holographic superconductors and trying to understand non-Fermi liquids. Also trying to think about holographic jewels of problems we're interested in, such as Luttinger liquids and Fermi liquids, etc., etc. I'm not going to go down that tack here. Okay, what I'm going to try and do is just simply start from the ADS-CFT correspondence and see if we can actually start to make contact with things that we know from integrability, and as I said, generalize them. And the main focus of this workshop is to understand non-equilibrium problems, and I'm going to try and argue that these methods are absolutely tailor-made for looking at problems far from equilibrium. So just to give you a very brief orientation for this ADS-CFT correspondence, the idea is that as a condensed matter physicist, you're interested in some theory living in d+1 dimensions, and the idea is that this strongly interacting quantum system can be recast as a theory of gravity living in one higher dimension. And so this extra coordinate is normally parameterized by z or z, depending on where you live. And the idea is that there's a correspondence between this high dimensional theory and the quantum theory that you're interested in that's enshrined in this so-called Gubser-Klebanov-Polyakov-Witten formula, which tells you that the partition function of your boundary theory is related to the exponential of some classical action residing in this higher dimensional space-time. And this little approximately equals to is just to remind you that usually people apply this correspondence in the so-called large N limit, where you imagine you've got some strongly interacting gauge theory living on the boundary, and the large N controls the saddle point, which gives rise to this identity. So as a condensed matter physicist, you see this and you think, well, actually, if all I'm going to do is large N, I might as well do mean field theory. One of the issues in this kind of approach is that usually in the large N limit, these are very strongly coupled theories. So actually, it's not always immediately obvious that you can use mean field theory. And in addition, we wanted to actually show that even though these results are obtained often in large N limits, you could still make contact with results at low central charge that might be more interesting to condensed matter physicists. And so I'm going to try and give you an illustration that this is actually possible. So the idea then is that there's a kind of field boundary correspondence, a kind of operator correspondence that relates fields in this higher dimensional space-time to operators and physical observables living on the boundary. And there's an expansion in powers of this coordinate z whose coefficients tell you about physical observables in the boundary theory. Okay? So for example, if this was the time dependence of some gauge field living in this higher dimensional space-time, the expansion is something like mu minus rho z, where mu is the chemical potential and rho is the corresponding charge density. So there's a source and bev. Okay. So why is it useful? Well, it's useful for non-equilibrium systems because what we're going to do is we're going to recast the problem of looking at quantum dynamics in a strongly interacting system as the solution of classical Einstein equations in one higher dimension. And also finite temperature appears in a rather different way than we're used to in conventional field theory approaches, in that finite temperature appears not by working in Euclidean space-time, but by incorporating black hole solutions into this gravitational problem. Okay? So that means it's actually very useful for non-equilibrium problems because you don't have to analytically continue back from imaginary time to real time. You can work at finite temperature and look at the real-time dynamics. And in particular, ADS-CFT doesn't really care about dimensionality particularly. So that's going to give us the ability to anchor the results to exact results that are known in 1+1 dimensions, but rather crucially gain some intuition for how to generalize these to higher dimensions where there's very few other techniques. Okay? So I haven't been here for the first couple of weeks, but presumably you had a lot of talks on looking at quantum quenches in the condensed matter context. So the idea being that you prepare some system in an initial state of a Hamiltonian with some parameter g, and you abruptly change the parameter g to some new g prime. It evolves under the quench, and you're trying to tease out some universal features that arise from this dynamics. Okay? So a lot of the activity has been looking at problems related to thermalization, or perhaps its absence in one dimension due to the proliferation of conservation laws. And this approach, this holographic approach, is going to be very useful for looking at thermalization type problems because it's very much designed for looking at time-dependent problems at finite temperature. Okay, so you'll have seen these kind of nice pictures that show kind of colliding Bose condensates which don't equilibrate over many thousands of collisions associated with the proliferation of conservation laws in these integrable low-dimensional systems. Now, in the high energy context, people have also been looking at thermalization, but from a rather different vantage point. They've been interested in trying to understand properties of the quark gluon plasma. What happens if you smash together heavy ions? You go through this intermediate stage of a kind of hydrodynamic evolution. And so in that regime, high energy physicists are trying to apply methods of hydrodynamics and fluid dynamics to situations where a priori you wouldn't have imagined high energy physicists looking at problems in fluid dynamics, okay? So problems related to kind of the entropy viscosity ratio are therefore very interesting in connection with these heavy ion collisions, and people have been trying to tackle these from different vantage points, both within ADS-CFT but also within pure hydrodynamics. So just to kind of give you a little bit of kind of overview of the high energy literature, there's a lot of work on looking at thermalization and strongly coupled gauge theories, for example, by Chesler and Yaffe and company. People have also looked at these quantum quenches. What happens if you start in a holographic system and, for example, abruptly change the metric? How does your system evolve as a function of time? And also from the perspective of hydrodynamics, because there's a very deep relation between the solution of the Navier-Stokes equations and the solution of the Einstein equations in one higher dimension. Okay? So in the condensed matter context, people have also been trying to use these things, and the main kind of rationale is that, you know, if you're trying to understand the dynamics of a strongly interacting system, you know that very often the microscopic degrees of freedom in your system are not very useful for understanding that dynamics. And so the idea of this holographic correspondence is that maybe the black hole physics gives you paradoxically a little bit more intuition about the dynamics of these quantum systems. Okay, So some illustrative examples, so there's nice work by Andrew Green and Julian Sonner, for example, who looked at non-equilibrium transport and trying to relate the noise in that to properties of Hawking radiation. So I was also involved in collaboration with Ben Simons, Jerome Gauntlet and company on looking at the dynamics of holographic superfluids. What happens if you perturb one of these systems? The idea is that the late time dynamics is encoded in the breathing modes of these black holes. So they're a proxy, if you like, for quasi-particles. Okay, so you don't have a natural quasi-particle description in some of these CFTs, but the breathing modes of these black hole solutions gives you some insights into the late time dynamics. And more recently, people trying to look at superfluid turbulence have argued that perhaps you can relate things like Kolmogorov scaling to fractal properties of black hole solutions. Okay, so in all of these examples, you're trying to use the black hole information to give you a little bit of intuition for what goes on in these diverse problems. Okay? So as I said, we're interested in problems of thermalization, right? So if you kind of step back a little bit as a condensed matter physicist and say that you're interested in thermalization, what you would do is you would just take two blocks of matter at two different temperatures, join them together, and that's what happens. So if these are very large, okay, the idea is that actually rather than just thermalizing, okay, you'll actually develop a non-equilibrium steady state where these two systems behave like their own heat baths, and I'll return to that in a little moment. So what it means is that the setup is going to actually be very useful for looking at non-equilibrium transport. Okay? So from the perspective of ADS-CFT, this is also particularly useful because if you're looking at energy flow at finite temperature, we can study this within the simplest example of a holographic system. Namely, we can study this within the framework of pure Einstein gravity. Okay? There's no matter fields, there's no charge fields, there's just nothing else apart from gravity. So this is the usual Riemann-Hilbert action with scalar curvature and a negative cosmological constant. I should say this antidescendant spacetime is a spacetime with a constant negative curvature, so this is usually negative in some appropriate units. And the idea is that this gravitational problem that lives in this higher dimensional system, the metric is dual to the energy momentum tensor that lives on the boundary. Okay? So it says that if you want to understand then energy flow in this strongly correlated system, you can think about it from the perspective of solving the Einstein equations for pure general relativity in one higher dimension. Okay? So we want to see whether or not this is possible, whether or not we can make contact with exact results coming from integrability. And as I said, because the ADS-CFT correspondence doesn't really care very much about dimensionality, we'll also start to be able to get some handle on the higher dimensional setups as well. Okay? So I should stress as well that the energy momentum tensor we're talking about here is not the energy momentum tensor that usually appears on the right-hand side of Einstein equations. Okay? So normally when you think about general relativity, you think about matter creating some curvature in your space-time, and the energy momentum tensor refers to this matter field. Here we don't have any matter fields at all in the gravitational description. The energy momentum tensor that I'm talking about here is the one that is dual to the metric via the ADS-CFT correspondence. Okay, so it's just pure gravity. Okay, now for this talk, I'm not going to talk very much about the solution of these nonlinear equations. But it's worth pointing out that actually, although you can write down the Einstein equations in this very compact notation, anybody that's done calculations in general relativity realizes that these things actually harbor very complicated, highly nonlinear coupled partial differential equations. And so simply sitting down and solving these equations analytically is in general very hard. Okay? However, there's been a lot of progress, for example, in using techniques of numerical general relativity, NGR, which in principle allows you to study these equations in quite a lot of detail. Okay? We're not going to go down this route here, okay? But it's worth pointing out the fact that, if you're facing some interacting quantum many-body problem, actually very often it's not immediately clear how to actually set up the problem and study it and understand the time dynamics. In some of these holographic systems, actually, as long as you can write down the Einstein equations, at least in principle, you can imagine trying to solve these partial differential equations numerically to tease out the long time behavior. Okay? So what are we going to do, right? So this work was actually kind of motivated by this very nice paper by Denis and Benjamin on energy flow in non-equilibrium CFT. And what they showed is, just in the context of conformal field theory, nothing to do with ADS-CFT, that if you take two one-dimensional quantum critical systems at temperatures T left and T right and join them together, you can give rise to this non-equilibrium energy flow that only depends on the central charge of these systems and powers of the temperature. Okay? And I'll show you that in a moment. The idea is that you join these two very large systems together and some energy flows from left to right, and if these systems are very, very large, there's a broad range of timescales over which the system doesn't realize that it's got finite size, and so you get a non-equilibrium energy current flowing between these reservoirs. Okay? So if you're interested in quenches, you could regard this as a local quench in a homogeneous system where you abruptly turn on a step profile, for example. Or you could equally imagine it being a quantum quench where you just turn on some coupling between these otherwise independently prepared systems. Okay? So as I said, what they showed then is that you get this nice non-equilibrium steady state, which is proportional to T left squared minus T right squared, with a coefficient that is completely universal and doesn't depend on any microscopic detail. Okay? So for those of you that have done, kind of finite size scaling in the old days before people started looking at entanglement entropy, usually you would extract the finite size corrections to the ground state energy and extract the central charge. That normally comes with the characteristic microscopic velocity of the system, and so it's technically non-universal unless you know something about the velocity. Here, the microscopic velocity doesn't actually enter the expression, and so this non-equilibrium result is actually truly universal and free from microscopic details. Okay? So one interpretation of this result is that you can think of this as being a kind of one-dimensional analog of the Stefan-Boltzmann law. You normally think about black body radiation going as t to the 4, so this is going as t to the d plus 1 because your system is conformally invariant, and you can think of this as two black bodies that are radiating energy, and so you get something proportional to t left squared minus t right squared. Okay? So the first thing we're going to try and do is tease this result out from the ADS-CFT correspondence. And in fact, this way of looking at the problem actually gives you a little bit more intuition for this problem than you get just simply by using methods of integrability. Okay? So I'm not going to kind of dwell on this very much, but since a lot of people in the audience are actually kind of interested in kind of low-dimensional quantum non-equilibrium systems, it's worth just briefly commenting on the fact that actually I think the main thing of Benjamin's and Denis' paper was actually not just to look at the average energy flow between these baths, but they also computed the full distribution of full counting statistics in this problem. You can look at the entire distribution of energy fluctuations across the interface, and they showed that you could compute the generating function for energy flow, so represented by delta QT, so Q could be in principle any conserved charge. Here we're thinking about energy flow, with some parameter Z, which is your kind of counting parameter. And so if you expand this result in powers of Z, the idea is the leading coefficient tells you about the average energy flow, and the higher powers tell you about fluctuations in the system. Okay? So it says everything you want to know about the energy flow between these connected CFTs you can compute, and there's a nice interpretation in terms of a classical Poisson process describing the energy flow across the interface. Okay? So just to kind of briefly comment on just one thing, I mean, these kinds of results are actually very important experimentally. I'm going to skip over the transparencies for the purposes of this talk, but if you just imagine taking this result and expressing it in terms of the sum and differences of the temperature, then you could recast this as some coefficient times delta T, the difference in temperatures between the reservoirs, and this coefficient is referred to as the quantum of thermal conductance. Okay? And so notice in particular that it depends on the temperature of your system. If you think about quantum of electrical conductance being E squared upon H, that's obviously kind of completely universal. Here you're transporting energy, and so it matters that you're at finite temperature. And there's kind of early work, including members of our audience, who looked at thermal transport in these kind of setups, and related it to kind of properties of kind of conformal anomalies and quantum transport. Okay, so as I said, I mean, you can look at this experimentally. Let me just show you one slide and I'll skip over the others. This was just some very early experiments where they had little suspended nano devices. These devices had kind of flexural degrees of freedom, so you could look at transport of these collective excitations. And what you see is if you look at the thermal conductance at low temperatures, it saturates at 16 times the thermal conductance quantum, because each of these channels had 4 degrees of vibration, and there were 4 of these little suspended devices. Okay? So you can actually measure experimentally these properties, and more recently they've looked at this not with 16 channels, but at the single channel level for electronic transport. And I'm going to skip over those transparencies and we can chat about them later. Okay, so you have this prediction from CFT. This has also kind of attracted a lot of interest from a numerical perspective, because you can imagine that you can start to use these results now to kind of benchmark developing numerical simulations in things like time-dependent DMRG. Okay, so for example, if you were to connect 2 quantumizing models together at their critical point, you should get this result of Benjamin and Denny with C equals a half. On the other hand, if you were to connect 2 anisotropic Heisenberg models in their gapless regime, you ought to get that result with central charge 1. Okay? So you might have heard some talks from Joel Moore and his collaborators at the conference. This is showing you some numerical simulations done on the XXE spin chain, where you look at the energy flow across the interface as a function of the right reservoir temperature, and you can see very clearly that you approach a steady state solution for different temperatures. Okay? These other plots are showing what happens if you add additional perturbations that break integrability. They're adding dimerization or staggered magnetic fields. You can see that actually if you really break integrability quite badly, then you don't approach a steady state at late times, as you would expect. You've modified the conservation laws in your system. But on the other hand, I mean, it's quite surprising perhaps that even over a kind of broad time interval, actually, at least at intermediate time scales, you still get something resembling the steady state, even though at late times you probably expect there not to be a steady state if you break integrability in this problem. Okay?
No, you expect there to be a steady state, it's just
well, so indeed, so not necessarily a steady state with these properties. Okay. So here we're talking about always ballistic transport in this system, and at late times in the vicinity of this interface, you expect a spatially homogeneous steady state region to form, and we'll try and understand this also holographically. But actually, I mean, one problem I should say is that obviously if you do start to add perturbations to these problems in 1D, obviously you've got a very demanding problem to try and solve to understand what the steady state is, does it exist, and what its properties are. Okay, so for example, in the case of XXE, I'm not sure if that was ever sorted out fully, even in the integrable case, if you look, for example, in the massive regime rather than in the case of the CFT. Okay, so just to kind of show you just a little bit more of that data. So here, you know, what you're saying is the average energy flow at late times is the difference of 2 functions depending on the left and the right reservoir temperatures. And if you, for example, fix one of the reservoir temperatures and change T right, you get some profile. And what you can see is that all of these curves are basically translations of each other, indicating that your energy flow is just the difference of 2 functions characterizing your 2 bands. Okay, and it's probably worth pointing out that actually I think some of these ideas generalize not just to CFTs but also to other integrable problems and also to higher dimensional problems. If you think about the interpretation of the 1D result, what it's saying is that you have some equation of state for your left reservoir, some equation of state for your right reservoir, and you're looking at the difference of the energy flow between these heat paths. And at least in the CFT, you get this simple result that you have a difference of these flows. Okay? Now, in higher dimensional cases, and also when you depart from integrability, it's not immediately clear that you have this simple left-right factorization, and in general, you don't. But nonetheless, there's some growing evidence from a variety of different vantage points that knowing information about the thermodynamic properties of your baths gives you very strong constraints on the non-equilibrium properties of this steady state. Okay, so for example, there's recent work done by Benjamin and Denis, for example, looking at perturbed CFTs. I'll also show you how this comes out in the context of the ADS-CFT correspondence, which shows you that some of these thermodynamic arguments apply much more generally to quantum many-body systems. And so there's actually potentially a lot of opportunities for looking at combining hydrodynamics and thermodynamic arguments to understand the late-time behavior of quantum many-body systems, both in 1D and in higher D, and also in the presence of perturbations, because in essence what they're doing is they're modifying your equation of state of your reservoirs. Okay, so let me get on then to this ADS-CFT part and explain how this goes, right? So in the 1D case, right, let's just think about this for simplicity to start with. You have two systems at two different temperatures. You join them together at time t = 0, and what happens is that you have a steady state region that grows out from the interface with a characteristic velocity that is the speed of light, the effective speed of light of your system. Okay? So in this region, right, your energy transport is governed by the results that I showed you before from Benjamin and Denis, and this region is also spatially homogeneous. Okay, so in the 1D case, this forms instantaneously. Okay, you've got some light cone propagation. The steady state region builds up immediately on connecting the two systems together, and what we're trying to describe are the properties of this steady state region. Okay, now in an ideal world, what I would do is I would connect two systems together holographically at different temperatures, so perhaps having two different black hole solutions. I'd solve the full Einstein equations for those initial conditions. I would show you the build-up to the steady state, and then I would then describe its properties. Okay, that's not what we're going to do. What we're going to do instead is we're going to say, well, look, if this region is spatially homogeneous and we're describing a non-equilibrium steady state, why don't we see if we can describe this, first of all, using these methods, and then we can always perhaps return to the full dynamics using holography at a later date. Okay? So that's the first simplification. Okay? So what does that buy you? Well, actually it buys you quite a lot, because if you look at the solutions of the Einstein equations in this higher dimensional setting, or even in the 1D case, okay, let me just go back. I mean, you can also ask the same question in the higher D case, so I'm showing this by having some spatial extent in these transverse directions. We still get a spatially homogeneous steady state forming at late times. It just doesn't necessarily occur instantaneously over the whole system as a result of applying this abrupt quench. Okay? But asymptotically, you're still going to expect a spatially homogeneous steady state to occur at late times if you have ballistic transport. Okay? So if you now try and look for such solutions, okay, so you're going to demand that the corresponding energy momentum tensor on the boundary corresponds to a spatially homogeneous solution. If you ask, how can you tease out such solutions from Einstein equations, it turns out that the way of doing it is unique. It says that the only way to get a spatially homogeneous boundary state that carries a non-trivial energy flow is to run past a black hole. Okay? So what I'm doing here is this is an expression for the metric in this higher dimensional system. So it depends on this extra dimension z, it depends on the transverse coordinates, and I'm labeling x as being the coordinate along the system. Okay? What it says is that we're running past a black hole solution, and theta is the boost rapidity. Okay? So if we set theta to 0, we wouldn't boost, and if we have a non-zero, it's corresponding to running past this black hole. Okay? So if you trot through the ADS-CFT correspondence, what I said is that the expansion of your fields in this higher dimensional space-time, their coefficients tell you about physical observables in your boundary system. It says that if you take this metric and try and isolate the coefficients close to the boundary, you can extract the steady state energy flow that corresponds to this kind of metric. Okay? So Okay, there's a lot of technical gymnastics for how you do that, but the upshot is that if you take this solution to your Einstein equations and you ask, what do you get out on the boundary? Well, actually, what you get out on the boundary is perfectly transparent. It says that you get the energy momentum tensor of a so-called perfect fluid, okay, with vanishing viscosity. So U is some kind of velocity of your flow that's related to your boost rapidity. And if you look at the expression for, say, the energy momentum for the energy flow in the x direction, you get this relatively simple form that depends on this boost parameter. Okay? So just to remind you, the internal energy density of a CFT goes as T to the D plus 1. This is the analog of the Stefan-Boltzmann law. And what it's saying is that you get this internal energy density multiplied by your boost factor, and therefore you get a steady state current. Okay? So how do you make contact with the results in 1D? Well, you have to identify what this boost parameter is. Okay? And it turns out to be relatively simple. If I imagine that I run past a thermal state at some temperature T, okay, what you see is you're going to see Doppler shifted radiation as a result of running past this black body. And in front of you, it's going to be Doppler shifted one way. Behind you, it's going to be Doppler shifted the other way. And so if you use the kind of Doppler shift arguments, you can convince yourself that if you run past a state at temperature T, okay, remember this energy momentum tensor only depends on this parameter T, okay, the temperature, the Hawking temperature of this black hole, we don't actually have a T left and a T right because we didn't actually specify that. We're just looking at a spatially homogeneous solution, and we've just argued that the only way to get a non-vanishing energy momentum tensor is to run past a black hole solution at a given temperature T. It turns out that the left and right temperatures are related to this temperature T by a kind of boost factor. Okay, so you're kind of Doppler shifting the radiation, and you're seeing different effective temperatures in front of you and behind you. Okay, so if you take this this identification, and in particular, if you also read off this coefficient, okay, so this coefficient is effectively counting the number of degrees of freedom in your CFT. Okay, in the case of a 1 + 1 dimensional CFT, this will be related to the central charge. In general, in this higher dimensional case, it's some kind of generalization of the central charge, which is counting the number of degrees of freedom that are contributing to your internal energy density. But when you do the ADS-CFT correspondence, this is not some arbitrary number. Okay? So if you did hydrodynamics, for example, for a perfect fluid, you could happily write down this form of the energy momentum tensor. This would just be the equation for the stress tensor that you would take out of Landau and Lifshitz, but this coefficient wouldn't be determined. It would be just some phenomenological parameter. Here, this depends on your coupling constants in your gravitational problem, and L is this so-called ADS radius that tells you about the kind of specific form of your anti-de Sitter spacetime. Okay? But what's known is how to relate this coefficient to the central charge in one dimension, for example. And if you combine these two results, you get precisely the results that were obtained using integrability. Okay? Now, in particular, you learn something new. Okay? What you learn is that if you multiply these two things together, okay, you see that the temperature of your black hole corresponds to square root of T left, T right. What it says is to get this steady state energy flow, you can equivalently think about running past a thermal state at an effective temperature, which is square root of T left, T right. Okay? Now, it's worth reminding you that actually if you connect two bodies together and they thermally equilibrate, they normally thermally equilibrate to the average temperature. Here, this is the temperature that two systems would come to if you connected them by an ideal Carnot engine. Okay, so I think there's actually some deep relationship between kind of thermodynamics and Carnot type reasonings here. Okay, and I'll kind of come back to that maybe a little bit later. But the upshot is what this black hole is telling us, this way of looking at it, is that this non-equilibrium steady state that forms in this one-dimensional quantum many-body system is equivalent to running past a thermal state at this temperature. Okay? Now, if all you looked at was the average energy flow, that maybe wouldn't be so much of a big deal, because you can imagine if you just run past some energy density, you're going to get an energy flow, and presumably if you varied the energy density or you varied your boost velocity, you would get any kind of steady state current you want. What's more interesting is that not only do you get the correct average energy flow, you also get the full distribution of full counting statistics. So if you look in Benjamin and Denny's paper, they give an expression for the steady state density matrix. They say we've got some non-equilibrium steady state and we want to know the properties of that steady state, so we need to have some steady state density matrix. It turns out that that steady state density matrix can be interpreted as a Lorentz boosted thermal state, because if you look at this density matrix, they didn't write it down in this form, but if you look at the density matrix with the benefit of hindsight, what you see is you're essentially taking a Boltzmann distribution, e to the minus beta e, and you're Lorentz boosting it by mixing in some component of the x component of momentum. Okay? So this is like a very highly reduced form of the GGE. Okay? So what it says is that all the cumulants of the energy flow are described by this very simple Lorentz boosted thermal state. And this will turn out to also apply in the higher dimensional case. And the name of the game then is to kind of pin down the effective temperature of the system and how fast you need to boost past it in order to reproduce these results. Okay? An obvious difficulty in the higher dimensional case is you don't have very many things to compare with, whereas at least in the 1D case you can compare to results coming out of integrability. Okay? So let's have a look then at the higher dimensional case. Okay? So what I argued was that in the 1D case, the way this steady state forms is by light cone propagation of wavefronts emanating from the interface. Okay? So a very natural thing to look at in the higher dimensional case is that you have idealized planar shock fronts emanating from this contact point with velocities that, at least at the moment, are not determined. Okay? And what you're trying to do is to understand what is the form of the average energy flow in this intermediate region. Okay? And the basic idea is that if you know the equations of state of these reservoirs, and you know that you're described at late times by hydrodynamics, okay? So depending on the problem you look at, this may or may not be true, okay? But what I tried to show you was that at least in these holographic systems, we did a computation of the energy momentum tensor, and you get the energy momentum tensor of a perfect fluid. And it's well known in problems related to gauge gravity duality that these strongly coupled gauge theories are very rapidly described by hydrodynamics. That's why you can apply these ideas to things like the gluon plasma. And so for a lot of problems, you're going to very quickly enter into a hydrodynamic regime, and so therefore you could equally do hydrodynamics. Okay? So what is the message? Well, the message is that if you have such a configuration with some outgoing shock waves, and you know the equation of state of the reservoirs, then energy momentum conservation across those shock fronts constrains the form of the steady state. Okay? And I think what's surprising is that similar constraints are also coming out even in the one-dimensional case, where it's not immediately clear that you can apply hydrodynamic techniques. But as I said, for example, after this work was done, Benjamin and Denny looked at the perturbed CFT in 1+1 dimension and showed that indeed you can think about the problem by thinking about the equations of state of the reservoirs, and this does actually give you very strong constraints on the form of the non-equilibrium steady state. Okay? Now, I should say at the outset, there's actually a subtlety here, okay? And it actually needs a little bit of revision, and I'm going to explain this as I go along. But actually, the idea of an infinitely sharp shock wave, you have to be very careful. So in a realistic system that had viscosity, you would naturally expect these shock waves to broaden as a result of viscous corrections. Okay, so this is something we noted in our first work of this problem. Actually, when you look at the solutions of these continuity equations, you also have to think about thermodynamics as well, and entropy production. And it turns out that actually the idealized infinitely sharp shock wave runs foul of thermodynamic considerations. And you have to include broadening of these shock fronts even in the absence of viscosity, okay? So what does that do for you? It replaces this left-going wave by what's known as a rare refraction wave, okay? This is something that's known in the context of hydrodynamics. It says that actually this infinitely sharp shock wave has some broadening, but nonetheless, the idea of integrating the energy momentum conservation across some shock fronts is clearly going to give you the same kind of physics when you're asking about the properties of the steady state, okay? So it's absolutely the case that if you modify the form of the shock waves, you will modify, in general, the form of the energy momentum current you get in this interior, because it affects your integration across those shock fronts. What it doesn't do is change the existence of the steady state or how you go about trying to calculate the properties of the steady state. Okay, so there's some technical issues associated with solutions of hydrodynamics when you meet these problems. You have to not only think about solutions of the equations of motion, but you also have to pay close attention to thermodynamics. Okay, but nonetheless, the prescription still carries through. Okay, so what I'm going to do is I'm going to first of all show you the idealized solution, because it has a very clear connection to the 1D results, but also, rather surprisingly, or perhaps not so surprisingly, it is also incredibly good agreement with the full solution involving rare refraction waves, okay? And I think it's just partly because, yes, you've got some small broadening of this left-moving inverted commas shock wave, but actually when you do the energy momentum conservation across it, actually it makes very little difference to the form of the energy momentum current, okay? So let me just first of all show you what you get out if you look at these idealized shock waves, okay? So this problem is enshrined in the so-called Rankine-Huguenot equations, which tell you that if you're thinking about a problem involving shock waves, you should integrate the energy momentum tensor across these shock fronts and demand conservation. This constrains for you the form of the steady state solution, okay? And what you can see immediately is that this isn't just simply t left squared minus t right squared, okay, or generalization to higher d. It's not just t to the d plus 1 minus t to the d plus 1. You have these denominator factors which are associated with the propagation velocities of these shock waves into the left and the right reservoirs. If you set d equals to 1, you get back to the result that we discussed previously, that it's just t left squared minus t right squared, and these velocities just reduce to unity, the velocity of light, okay? In the higher dimensional case, the idea is that you don't simply have this nice left-right factorization, which you would expect, and in addition, you get non-trivial propagation speeds because you're not just exploring the effective speed of light of your CFT, you've got some non-trivial propagation speeds which are like non-linear generalizations of sound waves, okay? And in particular, if you try and understand the form of this energy momentum tensor and compare it with the form for a Lorentz boosted thermal state, you again come to the conclusion that it's equivalent to running past a thermal state at this same temperature square root of T left and T right, okay? Now actually this identification needs revisiting, because if you allow the broadening of the shock fronts, what I'm arguing is you have to revisit the form of the steady state solution, but you don't revisit the way you compute it, okay? It's still energy momentum conservation across these shocks. It constrains the form of the steady state, and the precise parameterization comes out a little bit differently, okay? So let me just first of all show you some numerics, okay? So this is what happens if you just solve the continuity equation for this perfect conformal fluid in higher D, so this is done for spatial dimensionality 2, and you have some particular temperature difference between the reservoirs, and you can see that you have some outgoing shock fronts, okay, with velocities that are prescribed by solving those Rankine-Huguenot equations that I gave to you on the previous transparency. If you then look at the form of the energy momentum steady state, you can see that there's a non-trivial energy flow that's well described by this theoretical prediction you get from the sharp shock front picture. Okay? If you go to larger temperature differences, you can again see the very good agreement with the numerics. Okay? You again see excellent agreement with the steady state. But what you can also see is that maybe there's some hints that actually you have to be a little bit more careful and think about broadening. Okay, so it's very hard to see on these kind of simulations, and as I'll show you, the differences between the two cases is actually incredibly small for the energy flow, but nonetheless you can see that you need to consider these solutions based on thermodynamics. Okay, before doing that, let me just show you just an extra couple of transparencies. I mean, what I'm showing here is solutions for just perfect conformal hydrodynamics, okay? So first of all, if you're interested in quantum many-body systems, I haven't shown you that if you take your favorite quantum many-body system, that at late times you're described by hydrodynamics. But if you are, you could certainly ask about what would you get if you looked at steady-state solutions to the hydrodynamics. Also, in addition, I should also comment, I didn't state this explicitly, we're not assuming the existence of a steady state in these solutions. What we're actually doing is, rather than taking a step profile between two reservoirs, you consider two different temperatures with smoothly varying initial conditions, okay? You solve the equations of motion and you ask, do you reach a steady state at late times? And what you see is that indeed you do, and it's well described by outgoing shock fronts emanating from the interface, okay? So there's no assumption of a steady state. This is just unbiased numerical simulation of conformal hydrodynamics, and you see that you're led to a steady state with certain properties, okay? The other thing to point out as well is that obviously if you have a quantum many-body system and you impose an abrupt temperature profile, then you might imagine that there's a transient regime before you get to a hydrodynamic regime where the temperature might have smeared out. And so it's actually not unreasonable to consider smooth initial conditions for your hydrodynamic simulations, because by the time hydro kicks in a realistic quench setup with abrupt boundaries, actually that profile you would have expected to be smoothed out anyway. Okay, so this is just to also show another issue, because you might wonder, and we did wonder, even in the absence of thinking about the broadening of these shock waves, that if you added additional perturbations, could you destroy this simple shock wave picture? Okay, and so this was just showing what happens, for example, if you apply a temperature profile that isn't smoothly uniform, but has a little wiggle in it, say, across in the direction of the sample. And what you see is that, sure, you affect the early time behavior, but you nonetheless approach the results that you get with the smooth initial conditions. And in addition, you can also look at perturbations not along the sample, but also along the interface. They might seed, as you can see, there's little ripples here, okay? They might seed some inhomogeneities, for example, in your initial time dynamics. But nonetheless, what you see is you do have still very sharp shock waves appearing. And even in the intermediate time region, even if you have spatial inhomogeneities at early times, you can also imagine integrating over those homogeneities and getting a spatially average result. And you can see that the spatially average results also approach the results in the absence of inhomogeneities. Okay? So what it says is that this is very robust. Okay? Nonetheless, in the absence of viscosity, it's not legitimate to consider an infinitely sharp shock front. Okay? It's actually replaced with what's known as a rare refraction wave, as I said. And the idea is that actually there's some smoothly varying profile, okay, in the vicinity of this contact point, okay, and you need to consider that when you solve the Rankine-Huggenot equations, okay. So I'm not going to show you the details of that here, okay. I think that's best left as an additional talk, but just to illustrate, this is the comparison between the energy flow across the interface for those two cases in D equals 2 and D equals 3. And you can see it hardly makes any difference whatsoever to the analytical form of the result, or at least to the numerical form of the results. I should be more careful. Okay. So that's the first thing. Okay. But actually, the rare refraction solution gives you an extra wrinkle that wasn't there previously in the simple shock picture. And it's the following. If you imagine that you have some kind of shock wave that's kind of emanating out from this region, and that actually is broadened, and it continues to broaden, what you can imagine is that at very low temperature differences, you might imagine, I mean, I'm not proving this, but you might imagine that somehow the shock waves don't broaden very much, and so they just propagate outwards, and so you're left with a nice homogeneous steady state, and there's some broadening of this left moving waves, but it doesn't affect any of your results. It just kind of, it leads to a qualitative shift, because the form of the steady state solution is shifted by the fact that you have to integrate over this smoother profile, but you get a steady state of a similar character to what you had before. The extra feature that appears is that if you go to large temperature differences, okay, so here are the numerical results in d equals 2 and d equals 3, and actually in all fairness, they're not that large. I mean, you're talking factors of 2, factors of 3. It's possible for this growing rare refraction wave to encroach the contact region, okay? So it means that you've got this left moving wave, it is left moving, and it's broadening, but it does so in such a way that it actually overlaps with the interface, okay? So this regime we have to look at in more detail. It's actually possible that this might also occur in one dimension as well. It doesn't occur in the CFT case, okay? You have nicely propagating shock waves, but you could imagine that, you know, there's nothing a priori that would stop you to have some spatially varying profile in a one-dimensional setting. And so it could be that if you looked at alternative equations of state, maybe it's possible for those sharply propagating light fronts, even in 1D, to actually have to be replaced on thermodynamic grounds by some spatially broadened rare refraction wave. Okay? So in a sense, when we look at this higher dimensional problem, what we're effectively doing is we have something that's kind of quasi-one-dimensional in a loose sense, in that we're considering propagation in one direction, but there is still nonetheless spatial extent in the transverse directions. And so you're naturally led to, if you like, alternative equations of state in your effective one-dimensional problem, which are leading to these differences, okay? And my guess is that if you think about it more carefully in 1D, it might even be possible to get these rare refraction solutions in 1D settings. And again, just to kind of emphasize, this hydrodynamic approach is readily generalized to other equations of state. Okay? We've looked at particular equations of state governed by ADS-CFT. We've shown you can make contact with exact results from 1 plus 1D, but some of these results also seem to carry through for perturbed CFTs in 1 plus 1 dimension, and potentially also in higher dimensions. Okay? So just to summarize, you know, we've shown that the energy flow is described by this Lorentz boosted thermal state. The way you fix the parameters is by appealing to hydrodynamics and using energy momentum conservation across these shock fronts. And we're trying to generalize this to other problems because basically the hydrodynamic approach can accommodate all sorts of differences. Charge noise is straightforward. You could supplement this by numerical GR and also try and understand fluctuations in more detail in these systems.
Yes, so in the end you mentioned the 1D case again for these rarefaction waves. Don't you expect in the perturbed CFT case, or?
So I don't know actually. So basically in the 1D CFT, it's just precise light cone propagation and nothing is seen. I haven't worked through Benjamin and Denny's paper in detail actually, so that I think independently they were just looking at, after their paper, what happens in perturbed CFT, and you do the calculation and it turns out that you again come back to a kind of thermodynamic perspective where the equation of state of your reservoirs is giving you your steady state. Now, whether or not in their particular example they had to include rare refraction solutions, I'm not quite sure. Certainly Ben was quite conscious of the possibility of these solutions. I should say that in this, when we analyze a steady state, the solutions to the Einstein equations are unique, but the solutions of conformal hydrodynamics, dynamics, are not in general unique. And you could imagine other types of solutions, let's say with 3 shock waves, for example. So Ben, for example, looked at those solutions in some detail. What we're now coming to the conclusion is that you might have to also supplement these kind of multiple solutions by thermodynamic considerations, right? I mean, how do you see that there's a problem, for example, with the ideal shock wave? It says it's not sufficient to just solve the continuity equation and to compare to numerics and get a good agreement. You have to think about entropy production at those shock fronts. And the point is that it's possible for the entropy production at this left-going shock wave to become negative, which is a signal that you have to replace it with a rare refraction wave. So my guess is that there must be some perturbations of CFTs or perhaps some other problems in 1D integrable systems maybe, where somehow the equation of state is such that if you look at the ideal sharp moving light front, that it could potentially run foul of the second law of thermodynamics and therefore of necessity get replaced by a rare refraction wave. Okay? So I don't know whether that is the case, it's just that we know that you have to take them into account in 1D and they're not there in higher D, but they're not there in the simple 1D case. I mean, in some respects, I mean, you know, it's kind of a, you know, it's a bit of a shame because actually, if you have the ideal shock wave picture, you know, you get results that are very, very closely tied to the 1D case. Okay, so on the other hand, you know that in a higher dimensional problem, okay, I mean, it's not unreasonable that you can make contact with the 1D case, but the higher D case shows up new features, and that's indeed what's happening here. Okay, but nonetheless, you at least have some tools that you can use to check for consistency of your solutions. Right? So it could be that, for example, in these soliton or multi-shock solutions, maybe some of them are actually just ruled out on thermodynamic grounds, and that you're forced to arrive at somehow physically motivated unique solutions. Because if you look at these simulations, I mean, as I said, this is, you just impose some temperature profile between T left and T right, you get a steady state. I mean, there's no evidence for 3 shock solutions appearing. Could you cook them up? Maybe. But maybe again they run foul of thermodynamics, and actually they're just not there in physically realistic settings.
What do these 3 shock or multiple shock solutions
So
correspond to? Physically?
Well, so that's the issue, right? So you see, if you think about the logic of the approach, right, what we're saying is, what you should do is you should solve these hydrodynamic equations with certain reservoirs. The problem is that's the full dynamical solution of these partial differential equations. And in general, if you just look at it as kind of system of partial differential equations, the solution of those equations is not unique. Okay? So, for example, you know, we had this nice solution in inverted commas to these equations of motion that's based on an ansatz that you have very sharp shock waves. Okay? So then you say, well, hang on, you know, you said that this is right, and you see it fits incredibly well, right, to all the data, large temperature difference, steady state properties, etc. But when you analyze it with thermodynamics, it's not a permissible solution because the entropy production associated with a left-going shock wave can go negative. So then you have to go and analyze it by including rare refraction waves. But then you say, well, hang on, I'm a kind of condensed matter pessimist, right? I mean, you know, how many solutions are you going to give me to the equations of motion? So what I'm saying is you can also think about solutions where you don't have 2 shocks, but you have 3 shocks. Okay? Now, my gut feeling is that if you have left and right reservoirs, okay, there's no a priori reason to get multi-shock solutions, but nonetheless, if you're a mathematician and you're interested in solutions to the equation.
If you would connect and disconnect in an AC way,
for example,
you get
right?
whatever you want.
For example, so, but again, you know, when you solve partial differential equations, you have to think about the boundary conditions and which solutions are selected, and I think that's part of the difficulty. So what I'm saying is there could be discrimination amongst a set of solutions from the perspective of your applied boundary conditions, but it could be that thermodynamic consistency adds extra constraints on those equations. Okay?
So there is no, I mean, it's not known which solutions you have to pick up. I mean, given your physical problem, I take 2 reservoirs with different temperature, connect them. In your correspondence, is it known or not which solutions you have to pick?
So what I'm saying is,
or you have some freedom?
No, well, so you have freedom in the sense that the solutions to the partial differential equations are not in general unique, okay?
Yeah.
And, well, so they're not unique. There do exist multi-wave-fronted solutions. Okay, but what I'm saying is that if you look at the numerics, you see, first of all, the simple ansatz, 99.9% gets it right. You then have to look with thermodynamics, and you realise there's a problem with the left-moving shock wave, and then it's broadened. And if you then look at that, I didn't show the data, but actually there's another implication, because you can also think about the spatial profile along the sample. So at late times, it clearly becomes spatially homogeneous, but at intermediate times, if you have this rare refraction component, you don't have spatial homogeneity. Okay? So it doesn't affect the predictions, because what we said is at late times it's spatially homogeneous. Okay? So you can check that as well, we've done that. So you can look at how the temperature varies along the sample, and the rare refraction shock solution is in very good agreement with the numerics. Okay? But if you ask me kind of at a technical level, can I kind of give you a rigorous proof that if you solve these equations with these boundary conditions, you're uniquely led to this solution? I don't, but it's ignorance on my part.
Can you compute full statistics for with this technique?
Yes, in principle, yes, but good. So there's actually another problem, right? So in the case of the 1D case, okay, so Benjamin and Denis used some kind of, I mean, essentially these fluctuations, about fluctuation relations, okay? So the point is that those fluctuation relations are derived by assuming that you have kind of parity symmetry in your resulting steady state. Okay. Now, at late times, your solution will be spatially homogeneous, and my guess is that that is just 100% correct. That the fluctuation relations must hold, and you can therefore derive the full form of the full counting statistics. I mean, another way to say it is that in their 1D case, knowledge of the energy current is enough to determine the full spectrum, because their higher moments are related by differentiation with respect to a kind of perturbed version of that current. So you get the average energy flow, you get the full spectrum of fluctuations. So we did similar things in our analysis, because actually, if the fluctuation theorems hold, then knowing the form of the energy current is enough to constrain the fluctuations. Okay? The problem is that if you have a rare refraction solution, you're no longer spatially homogeneous at intermediate times, and their trick of using parity to derive the fluctuation relations needs revisiting. But my guess is that it's a problem with the derivation rather than the result, because at late times, your system will be spatially homogeneous, and you will have this average energy current, okay? But that needs revisiting.
But it seems that, sorry, final comment, it seems that all your different solutions just correspond to different full counting statistics for the currents. I mean, you have the same average current,
Yeah.
but the tails of the spatial propagation are different, and therefore the higher moments.
But no, so not quite. Yeah, I mean, yes and no. So when we talk about full counting statistics, we're talking, in the simplest case, is just talk about what happens across the interface. Okay. More generally, you can ask about what happens in the steady state region. But imagine, for example, you have a rare refraction wave that overlaps the origin. So at short timescales, you're not technically spatially homogeneous. But as you wait longer and longer and longer, you will be, and then you discuss the full counting statistics in that region. So I wouldn't worry too much about the fact that, you know, because you've got spatial inhomogeneities over there, that as a result you can't meaningfully talk about full counting statistics. You can, so there will be a well-defined average energy flow and a well-defined distribution of fluctuations across that interface at late times when everything has become spatially homogeneous.
I have a very basic question. So you started by saying, so ABS CFT doesn't really have to do anything with integrability, so it's a
Yeah.
sort of methods, etc., etc. So as you showed yourself in Joel's data, if you break integrability, then the current just decays.
Yeah.
Okay, and so you basically end up with zero current.
Yeah, in this case, yeah.
Well, I mean, I think that this is what we expect on general grounds. Yeah. And so to what situations actually does the higher dimensional story really apply?
Well, so okay, so well, let me first of all actually answer that in a slightly different way. Even in the 1D case, I would say Benjamin's result I find slightly strange. Okay, so if you thought about it from the perspective of a kind of CFT, right? I mean,
But CFT is integrable.
it is, but what I showed you is that the steady state is described by Lorentz boosted thermal state with only two conserved quantities. Right? I mean, I find it a little bit surprising that you can't actually get a full GGE in that setup. Now, it could be that
This
maybe.
is just terminology. I mean, you can call it a GG because if you look at the free theory,
Yeah.
the steady state density matrix, you can interpret in terms of a regular GG.
No, I agree with that. So no,
But the same is true for the CFT, I'm sure.
No, well, okay. So all I'm just saying is that I mean I agree. I mean, so there's always a kind of question about when you look at conservation laws of kind of linear combinations of conserved charges. But all I'm just saying is that this is a particularly simple form of the GGE.
Yeah.
And all I'm saying is I don't know whether then that's actually because the resulting steady state when you apply these temperature differences somehow selects out a kind of subset of the kind of, you know, basically if you look to GGE, I mean normally you have all the conserved charges.
Yeah, but you have them here too, yeah, because you have to look at the modes, right? So it's basically M or delta times cosh. I don't want to call it theta, call it phi, whatever the rapidity variable, and it's for all the rapidities, so they enter there.
Okay, so fine. So but then there's another distinction as well. In the
So there's a regular GG.
No, that's fine. So in the higher dimensional case, right? Generally, you expect things to thermalize at late times, right?
Yeah, but that's exactly what I'm asking. So why does the current decay?
No, but thermalize and there's thermalize and thermalize. If they're finite and you join them together, then indeed the current will decay, right? Energy will propagate from the left to the right. But if these systems are incredibly large, it's like you're applying a heat bath.
No, it's the same in the 1D case. Well, we can talk afterwards, but in the 1D case, make it as large as you like. The current will decay.
Well, I mean, you still got. I mean, it's a CFT, right? I mean, so you've still got a conserved momentum, conserved energy, right? So maybe if you add some perturbation that destroys that, then okay, then maybe it goes away, right? I mean, so indeed, I mean, it's probably a question of what perturbations you add. Right? So actually, I mean, that was another thing that I thought might be interested in this kind of holographic context. I mean, actually, in principle, you're not. I mean, people usually refer to it as gauge gravity duality rather than ADS CFT because you're not necessarily having to deal with CFTs. So in principle, you can turn on all sorts of perturbations, and that's what happens. So indeed, you're probably right. I mean, if you kill the momentum current, you probably just decay to zero.
What determines the thickness of this shock wave? When you get is it a free?
Good question, actually. So we haven't actually.
It's a free parameter.
No, we haven't actually fully analysed that actually. And actually, I was chatting to Ben actually just before I came here actually to see if we could think about this. So what I gave you this qualitative argument, which I actually don't know 100% whether it's the correct way to think about this, but if you solve these Rankine-Hugenow equations, right? First of all, you've got a conformal field theory. So actually, you're forced to think about kind of scaling variant solutions. Okay, so they depend on kind of x over t in a particular way, and you have no freedom. Okay, but associated with that is some kind of width. Okay, and actually, this was precisely my question. Is that what I hadn't fully got my head around? Is that what I suspect is that it's this width that determines that you've got two regimes. Okay, so I think at small temperature differences, it must be that the width, in some sense, of this shock is sufficiently small. Okay, and in fact, you can see it here. I mean, when they're very close, I mean, it's hard. That's pretty good. When you go to the larger temperature differences, okay, maybe there's a slightly larger width. I think the point is that somehow the width of this region must get larger so that on the timescale of propagation, it starts to encroach the origin. Okay, we actually have a figure of this, so there's two different regimes. So in one case, the thing propagates away with some width that's located around the shock front. It's some particular scaling solution and a particular function of x over t, but I don't have a very simple qualitative handle on what actually controls that width, right? Because we don't have any viscosity. But nonetheless, it happens that there's two regimes, and I suspect it's when the width grows sufficiently fast that the kind of center of mass of the wave hasn't had time to shift out of the origin. It then just sits on the interface. And in particular, what that means is that you're actually going to get some power law approach to the steady state in that second regime. Okay? So in the 1D case, you just instantaneously end up in the steady state, whereas now the steady state will develop as a function of time, and there'll be some algebraic approach to that steady state. But we haven't finished analysing that. Yeah.
Well, it's a sort of cut-off effect that, I mean, in the original work by Doyon and Bernard and Doyon, they assume a boundary without a scale, so because it would break conformal invariance. Now it seems that in higher dimension you're forced to have a thickness of this layer that is a sort of cut-off.
Well, I don't.
Dependence. So
No, I'm not.
like a boundary that violates conformal invariance.
Well, okay. I mean, that might be implicit in some of the numerical solutions, but I don't think that can be the case. So let me put it differently. What we did is, I mean, here is a solution to conformal hydrodynamics with particular temperature profile. And you're right that if you impose a particular temperature profile, then you've introduced a scale associated with the width. Yes. But we also looked at what happens if you choose different interpolating initial conditions, and then the form of the steady state solution is independent of how you set that up. So you affect the short time dynamics, but not the late time dynamics of the steady state. Because somehow the kind of intuition is that the late time dynamics is governed by the fact you've got a bath with this equation of state, a bath with that equation of state, there's some propagation and a mess at intermediate times. But somehow the late time dynamics is saying, well, okay, I mean, you put this bath at this temperature, this bath at this temperature, and the steady state is somehow heavily constrained by that. So I don't think the length scale in the rarefaction wave is associated with the kind of the length scale over which your temperature profile varies. I mean, another reason is that they're kind of scaling solutions, so that the solutions are conformally invariant. I mean, in principle, you can think about solving the Riemann problem. I mean, in hydrodynamics, the sharp boundary problem is called the Riemann problem. Okay, it's just that for numerics, it's just easier to have some smooth interpolating conditions.
There were questions? Okay, we thank the speaker again.